In this video, we will discuss the simulation of a stress concentration, fatigue, and vibration with a cantilever beam in Ansys. We will discuss elements of SN curves and how we use them to predict fatigue life. We'll also create a simple geometry of a cantilever for us to analyze. And we'll show the effect of a stress concentration on this cantilever beam. We'll analyze modes of resonance. We'll induce excitation at a couple of frequencies for harmonic or frequency analysis, and we'll characterize fatigue life. This work is important for applications that go beyond the simplistic example that we're going to share here. You can think of examples in design of mechanical components, for example, using fillets on corners, aeroelastic flutter, vortex-induced vibration, machine fatigue, or structural analysis, like what you might see with a Tacoma Narrows Bridge. Now, in many of these cases, the details are more complicated than what we're going to get into here, but ultimately, we're looking at being able to reduce stresses by appropriate design of fillets, look at how to account for vibration and how that might induce failure due to fatigue in the long term or short term, depending on how it's being loaded and how it's being designed. If you like further information, I suggest that you take a look at the random vibration analysis in Ansys Mechanical from the Ansys courses. And also you might take a look at Juvenal and Marshek's book, Fundamentals of Machine Component Design. Well, what do we use an SN curve to do? We look at it in terms of counting the number of cycles that we will be able to have for a given amount of load. So we have what is called the low cycle strength for 1,000 cycles. We have what's called SN prime, or the RR more endurance limit, which is typically taken by a torsion or a rotational, it's a rotational bending experiment. And then we can use those results that give us the SN prime with some various factors, as you see here, to come up with what we'll call SN, which is known as the endurance limit. So you take the SN prime, or the RR more endurance limit, multiply it by something like the load factor, or the gradient factor, or the surface factor, or the temperature factor, and reliability factor. And for an ideal case, we can say that all these factors might be 1. The reliability is like 50%. Temperature is it's kind of standard. Smooth, it had to be, surface factor had to be really smooth. The gradient factor, typically kind of larger geometries where you're not going to have an issue in bending. And then the load factor is because we're doing this with bending. And what we get is a curve, or a line with a knee, where we have the S10 to the third, or the low cycle strength for 1,000 cycles up here, and then we hit what's called the knee, and down here we have the endurance limit at 10 to the 6, or 1 million cycles. Okay, so the way this curve works is if the loading is under the endurance limit, which is this SN right here. So like, let's say that the stress that you have is under the endurance limit strength, okay, right here, then we would suggest that for steel or many of these normal ductile materials that we're dealing with, you're going to have infinite life. If, on the other hand, you're going to have values that are above this SN endurance limit, say values that could go up to this S10 to the third value, okay, then what you would see is a prediction for the number of cycles we should have. So if you're at something between 10 to the third or 10 to the fourth, that's going to be considered low cycle fatigue and could be detrimental to the application that you're attempting to solve with your machine. Now, approximations for steel are as follows. If we have an ultimate tensile strength, we can say that the S10 to the third, or the low cycle strength for 1,000 cycles of fatigue, will be 0.9 times that ultimate tensile strength. This approximation comes from Juvenal and Marshek. We can also approximate the Sn prime, or the RR more endurance limit, by multiplying the ultimate tensile strength by a factor of 0.5. And so if we are given the ultimate tensile strength for the steel, we are able to say what the S10 to the third and Sn might be, assuming we also know what the appropriate load factors and surface factor and reliability factor and temperature factor and gradient factors might be. Okay? So we're going to do our example using the ultimate tensile strength for structural ASTM A36 steel. The ultimate tensile strength that we're going to specify is going to be 500 megapascals to make things kind of simple. So 500 megapascals, yes, the yield strength is 250 megapascals. The low cycle fatigue strength, or 1000 cycle fatigue strength, is going to be 0.9 times SU, which will give us 450 megapascals. And then we can figure out what Sn prime is by taking the ultimate tensile strength and multiplying by 0.5 and all these different factors. So when we do that, we get that Sn will be about 250 megapascals as well. So we can make our nice little Sn curve that looks something like this. So at 1,000 cycles, we have 450 megapascals up here, and at 1 million cycles, we have 250 megapascals. Now, the geometry, so actually before we pull in the cantilever beam, let's go ahead and put these material properties in Ansys. So to do that, we're going to open up a new workbench, and to get started, we'll use the static structural system, and we'll double click on engineering data, and we're just going to create a new material called generic steel, like that, and then we will bring in the density here, which is not necessary for all the static analysis, but it's useful for some of the vibration analysis. We'll bring in isotropic elasticity, and we will also bring in the Sn curve here. Okay, so the density, we can use 7850 kilograms per meter cubed. For Young's modulus, we can use 200 gigapascals. We can use a Poisson's ratio of 0.3. And then for the Sn curve, we're going to hit this tabular button here, and we're going to put in 1,000, so 10 to the third, 1,000 is going to be, cycles will be associated with 450 megapascals, so 450 E6, and 1 million, 1 E6 will be associated with 250 E8, or 250, sorry, 250 E6. That would be 250 megapascals. Now, for this plot here, we could put down, for example, 1 E8, for example, and that will then, and then we can put in like the same value again. Okay, but it doesn't really matter for this analysis. And my understanding is that Ansys looks at, if you plot a curve like this, it's going to look at the first and the last point here. Okay, so let's go ahead and we're going to delete this point right here, and this will be our Sn curve for our analysis. So we can go back to the and it's also not a bad idea to right click here and use this as the default solid material. We're not going to use structural steel here, which is the default Ansys gives us. All right, so now we've created the material properties appropriately, and now we're going to look at the dimensions for the cantilever beam we're using. So this cantilever beam is going to have some length and have some span and some thickness. We're going to apply 300 newtons of transverse load at the end initially, and we can predict already that if we apply this 300 newtons, we'll get 360 megapascals for the maximum bending stress. That will be either above or below the beam at the wall. So let's go ahead and do this analysis in Ansys. We'll create the geometry, and we'll use Design Modeler this time. And as we're bringing that up, we'll go back to the dimensions just so that we can try to remember them. Oh, or maybe we don't need to. We're ready. Okay. Let's see here. Good. All right, so that was faster than I thought. We're going to go to sketching, click on Z, and we will go ahead and do some drawing. We can do a rectangle here and come up on this. Oh, before I do this, go to units, make it a little bit easier. We'll use millimeters. Okay. So once again, we come over to rectangle, and we can do something like this. Okay. And we will make another rectangle doing something like this. Okay. So how are we gonna get these dimensions? We're looking at the profile, the side view of the rectangle that we're going to extrude out. So let's go ahead and make this the 15 centimeters or 150 millimeters. We'll make the thickness that we're interested in, whoops, okay, vertical, okay. This vertical dimension is supposed to be 5 millimeters. And we can go ahead and bring that dimension to half of that, which is going to be 2.5 millimeters. We can make this look a little bit nicer by giving it, whoops, let's see, well, yeah, I should have, either way, I guess we can do the general one here. If I do the general one, then let's say we'll make this, I don't know, 30. So let me, oops, that's because I hit mm, don't do that. And then we'll move this vertical up 15. Like that. Okay, I think things are pretty centered. They look pretty good. Yes. We have some extra lines that we want to get rid of. So we'll go ahead and go to Modify and Trim right in here. Like that. Okay. Another thing that we'll do here is add a fillet. Okay, and we'll put it right there, and we'll put another one right there. Okay, and for this fillet, we can add dimension of radius like that, and I'll be R7. Let's go ahead and crank it down to 1 millimeter. Okay, so that is now 1 millimeter that we're talking about. That's pretty small, and that's going to give us a stress concentration. We can go back to the modeling step, and we can see that we have a sketch here. We're going to go to Create, Extrude, and we'll click on the sketch. We'll apply that like so. And we will put a depth of 30 millimeters. So that should be just fine. We hit generate, and let's see if it did it. It did it. Great. Okay, so there's our geometry of interest. One thing that might be useful for us in a few minutes, we don't have to do it, but we can do it, is we'll go ahead and make this fillet radius a parameter that we can access from Workbench. Okay. And let's close this up. Okay, so now we've got our geometry, and we have this parameter set that we can if we double click on it, right, we can change the fillet radius, and we can make that our current one for later use without having to open the geometry. So now let's go into the model. And for this, what we're going to do is apply that transverse load, that cantilevered load of 300 newtons on the end. And what we expect is that we'll get a value that is at least 360 megapascals. And that's because we have the stress concentrator in the corner. So the geometry comes up, good, all right, or it's almost up, okay. We want to make sure that we have the use of our generic steel, so that's good. And we're going to mesh using an element size of, let's say, let's start with 4 and see what that looks like. Here it is. Okay, generate. Give that a second. Okay, so that's a little bit big, all right, especially if we want to get into that stress concentration. We'll go smaller, so let's go down to 2. And we'll generate like that. Okay, that's not too bad. All right, maybe we can go smaller. There's a little. Let's go a little bit smaller. Let's go down to, maybe we'll go down to 1, and let it give it some time. That'll double the size of the mesh, or not the size, but you know, that's like half the size and maybe double the number of elements. Okay, that looks pretty good. Let's go ahead and add a boundary, a fixed boundary on this end right here, and we'll go ahead and add a force on the right end. And it doesn't really matter if we do it up or down, but let's do it down. We're going to go in the minus y, and we'll do, we said 300, so minus 300. Okay, and then we're going to be looking at stresses. So we can insert equivalent of 1 Mises. We can also insert the equivalent, or the maximum principal. Okay, that would give us the bending stress. So let's see, it says, oh, fixed support, because I didn't click the ever important apply. There we go. And we'll solve. Okay, so I hit my limit on nodes. Too bad. So let's do 2. And let's now go to solve. Okay, and if we click on the maximum principal stress, oh, we get all zeros. Interesting. Okay, if we click on the equivalent stress, we also don't see anything very interesting. So what is going on? Where was this force applied? Oh, was it applied back there? That is not where we want it. So let's come back, because of course I made a mistake. Let's put it over here, and then hit apply here, and now we should be good to go. Okay, so I just want the whole thing though on this. I see that what it's doing. So let's go ahead and, so this one's on everything. Let's delete this. It's probably just faster to delete it and put a new one in that shows the equivalent stress on the whole body. We can retrieve the result. Okay, that was a little sloppy. All right, so what do we see here? We see that the equivalent stress, the von Mises stress, is showing a max of 427 megapascals. And if we go to the max probe, okay, it's on the top, kind of about where you would expect it, okay, up here, right, at the edge. And then the maximum principal stress is even higher at almost 500 megapascals. Now, we predicted that it would be 360 megapascals of stress, right, from this simple calculation. And that's because we weren't accounting for the stress concentration. So what can we do? Well, if we make the radius of curvature significantly larger, we can avoid this issue of having a significantly larger stress in that corner. So to do that, we'll go ahead and close and then go back into Workbench. We'll click on the parameter set, and let's go ahead and let's make this something like 10. Okay, so a radius of 1 centimeter. We'll go ahead, that'll be set as the current. All right, so because we changed it here, and then we can go back into our project, and it's going to say, oh, it wants to update some things. So we'll double click here on the model, and it should. Oh, did it not? It didn't say. Okay, so I maybe had to update things. It often will say, you have something that changed upstream, and now do you want to make those changes? It didn't do that, so then I will go here manually, and I will do update upstream components, or just update. We'll do update. Okay. And now when we open up the model here, yes, that's what I was looking for. And so without opening the geometry, if we did this correctly, our model should update to have this larger radius. Okay, and it's thinking, it's working on it. Okay, and it did. Okay, unintended consequence though, okay, this now is very thin. Okay, I don't think that will pose a problem for us, but it just looks a little bit ugly. Okay, I should have made it a little bit taller or thicker. Let's go ahead and proceed though and see what happens. We'll throw caution to the wind. Now, for this, we'll go ahead and we'll mesh. Now this could be problematic. Okay, let's see. All right, still looks pretty good actually. Let's see if we get a solution that runs. Yeah, that's really kind of ugly looking. When I did this previously, I used better dimensions, but it's okay. All right, so now what is our maximum principal stress? 370 megapascals, right? And we predicted 360 megapascals, and it's about in the right location. The equivalent von Mises stress, 332, so it's actually a little bit less. Remember, von Mises is looking at the maximum distortion energy, and so it's essentially looking at, hey, what's the equivalent stress to uniaxial loading using maximum distortion energy, and it's kind of a rough estimate, which is close to Tresca, which is half of the shear stress. So okay, so this is good enough for us to continue. So at this point, all right, if you are looking to submit the assignment, okay, you would want to have shown the effect of the concentrated stress in a tight radius of 1 milliliters, okay, and of 1 millimeter. And now we're going to move on to looking at estimated fatigue life, okay, with a static load of 300 newtons. So how do we do that? Well, let's look at it analytically first. If we go over to this slide, we said we had 360 megapascals, okay? And we also see that we have an SN curve going from 450 down to 250, 1,000 to 1 million. Where is this point? This point is somewhere maybe around here, right? It's between 250 and 450, okay? Now, I'd like to just kind of draw a line down and figure out how many numbers of cycles I'm going to, how many cycles we're going to get out of this simulation. Of course, with it being on a log-log plot, that calculation is a little bit more complicated. So what you see here is us taking the 360 megapascals, looking at the log-log relationship for an SN curve, and you can think of it as having a slope. We're just looking at this line, okay? So it's got a negative slope, and it's got a y-intercept, so that's the b, right? And so, if I had, it's like y equals mx plus b, right? But this is on a log-log plot, all right? And so if I have 2 points on a line, right, I can solve for the a and the b, right? And I do have 2 points. I know where SF is, I know where SN is. So you do this algebra out, and you can figure out what a and b are, like so. And so now we can define this line. And these are just this is a general approach to doing this. I can remember that I have my SN and SF, right? But I can still go a little bit further in terms of a general approach. So if I'm interested in finding out what the N is associated with a given S or vice versa, right? I can plug in the value here for our 360 megapascals and then solve for N, like we see here. So what is N equal to? Question, question, question. Well, for that, we have a short little MATLAB script, okay, that we've written here. So we have SN equal to 50 megapascals, SF equals 450 megapascals, and we're going to plug in our S of 360 megapascals, and it will tell us what the N is. Okay, and so this N comes out to be something like 14,000 cycles. That's great. That's fine. Okay, so if I were doing this just, back of the envelope calculation, we would be at 14,000. Now, if we look at what we got in Ansys, though, we got an equivalent stress of 330 or one of 370. And, we think, that shouldn't make that big a difference. But does it? So if we come over here, right, remember we had 14,000. Let me just put in 330. Okay. So we drop down to 330, and look, now we're up to 38,000 cycles. Okay. Just going from 360 megapascals to 330 megapascals. And if we go up to 370, right, we go from 14,000 cycles now to about 10,000 cycles. So we learn a couple of things here. One, this slope is pretty significant in terms of making a difference of thousands of cycles, okay? And if not tens of thousands of cycles, okay, at least in this portion. And the other thing is that it's because of this sensitivity and because there are variations in material properties and there can be variations in load, there's going to be a large degree of uncertainty in the low cycle fatigue range for when this system is going to potentially fail. So typically, we want to make sure that we are not designing for low cycle fatigue, right? That you're designing so that you're underneath the endurance limit. Because if you design here, you don't know exactly how many cycles you're going to have. Now, if you keep things very controlled and you want to have planned obsolescence, you can do quite well, right? In terms of having to have replacement parts. But typically, we want to avoid designing for this range, right? So we got values ranging from 10,000 to 14,000 to 38,000, okay? using our simulation and using our analysis. So how do we do this though in Ansys? It's kind of like a fun little add-on that they have here. If you come over to solution, you can insert the fatigue tool like you see here, and then you can come in and we are going to insert the life, okay, like this. And look, under fatigue tool, it's going to give us some options here for the type of analysis that we're going to be using. Now, mean stress theory, if you start doing things with like Goodman lines and things that we cover in our design mechanical components class at Rutgers, you could, and you know, when I've taught these DMC, we go through, you know, the fact that the crack is going to be opening or progressing more as we have it under tension than we have it under compression, and so these Goodman lines allow us to come up with kind of equivalent degrees of alternating stress for a given amount of offset from zero. Compression, right, is not going to cause the crack to progress as much. But here for us now, we see we can either use equivalent von Mises or we can use these others. Actually, you probably can't see that. Let me bring that up. If you go down, right, you can see that we can also use the maximum principle. So we see that maximum principle is going to, at least from what we saw, it's going to be telling us that we're going to be failing sooner, or like 10,000 cycles, opposed to the 14,000 cycles we predicted by hand, as opposed to the 38,000 cycles that we have if we use von Mises. So let's see what happens. We're going to hit evaluate here, and we're going to see this nice little plot. So what does this mean? Well, it means that out here where the stresses are fairly low, we have essentially infinite life, 1 million cycles, okay, the dark blue. But then as we zoom in, okay, to this region near the base, or near the fixed support, what do we see? We see that we're in the red, and we have 9,441 or so cycles of life, right? And what did we say before? We said that 10,000 about, if we go back to MATLAB, about 10,000 cycles, or 9,978, okay, were associated with this stress value of 370 megapascals. Okay, so this is pretty cool. And if you're doing this, okay, you might use a screenshot, okay, along the top of the cantilever without a stress concentrator with a static load of 300 newtons, and to estimate the fatigue life according to our simulation. So for that, you know, you might come out a little bit and take that shot. And you know, you can also specify whether this is using the maximum principal stress or is using von Mises. So if I change it back over to von Mises here and come back down, and we're going to use the von Mises instead, equivalent, all right, and then we run this or evaluate it again. What do we see when we click on life? Wow, look at that, 35,625. What did we predict in MATLAB? We predicted about 38,000 when we used the 330 megapascals. So this is a nice way to check to see if we're on the right ballpark between analysis and Ansys. Okay, and we also are using this kind of nice fillet that allows us to avoid having a stress concentration there. In our objectives for this assignment, for this work now, let's take a look at vibration. Okay, so we go all the way back. Okay, we've done the simple cantilever. We've shown the effect of a stress concentration. We're now going to analyze modes of resonance. So for this, you can go back to Workbench if you want, or you can kind of do a console. where you come over to the analysis, and we're going to insert the modal analysis right here. Sorry. Okay, and so this, notice, it's often helpful to see, okay, where does this lead to? This is pulling in nothing from the structural, okay, but it is pulling in from the mesh and the geometry, okay. So if we come over here, okay, we've got to add a fixed support, and hopefully I'll do it right this time. So I do a selection here, apply, and then we don't need to add a force. We're doing modal analysis, right? So modal analysis is essentially saying, hey, if I were to shake this at different frequencies, show me which ones are going to have the largest deformation, largest displacement. They're going to kind of jump. They're going to bounce. Those aren't the right terms, but they're going to hit resonance, okay? And when you think about resonance, I think it's important, well, it's not bad to look back to your good old days with differential equations. And yes, we're doing PDEs and we're doing finite element, but if you think back to the old mass spring damper, the M right here, mx double dot plus bx dot plus kx, all right, and this is in transfer function form, but you see m, b, k, your second order system. And we assign a mass and a damping ratio, or a viscous damping B, K, the spring constant, right? We can figure out what the zeta, what the damping ratio is, okay, for this particular system. And we can also look at the Bode plot associated with this, right? So this is looking at the amplitude and the phase as a function of frequency. And at low frequencies, we're in phase. High frequencies, we're going to be 180 degrees out of phase. And at resonance, which for this system is just at 1 radian per second, okay, we have a spike in amplitude. Now, this spike in amplitude, if you're an electrical engineer, you use something called the Q factor, but mechanical engineers, we use damping ratio. And so this can be, for low damping ratios, this can be approximated as 1/2 zeta. The point here is that damping matters. And as you get closer to that resonant frequency, the amplitudes that you're going to be getting out of your system are going to be higher if you have a lower damping ratio. So in COMSOL, or in Ansys, sorry, there are ways to change both kind of the structural damping, the solver damping, actually there are 3, I guess, or material damping. Okay, so structural and mechanical, or structural material, and numerical. Really, I think they lump it into kind of material and numerical. But in order to figure out what the actual damping is, you need to do an experiment. And I don't have that experiment with this material to show you, but it's not bad, okay, to go in here, okay, and just, we can give it a damping. It doesn't make that much. Actually, for here, we'll just put in a structural. Actually, we're going to put. No, we can just put in. For this one, we'll just put in 0.01. Okay. So structural damping coefficient, just like that. And then when we run this, we want to look at the deformation. Whoops. Okay, like this. And hit solve. And I didn't change the settings, but it's going to look at the first 6. It defaults to looking at the first 6 modes of vibration. Okay. And this is going to just give us an idea of what frequencies are associated with the different modes of resonance. Okay. So if we click over here, okay, what we should see is it's calculated out a bunch of different modes, or 6 in particular, right, of resonance. You have one at about 200 hertz, one at about 1100 hertz, one at 120 or 1200 hertz, okay? And if you get rid of the damping, it doesn't make that much of a difference. We can do that here. I'll just say that this is 0 and run it, and it'll actually lower these resonant frequencies just slightly. In textbooks, what you'll find is some classical treatment to calculate out the first couple modes of resonance for a cantilever beam. And this is from Den Hartog's book, and what they say, what he says here is that we can estimate, or we can calculate out the first and second modes of resonance by these equations. And mu1 here is mass per length. So that would be the essentially taking the like the b times the h times the length, right, times the density, and then divide by the length, right? So you have essentially bh times density, and then you use that in here. And E and I, E is elastic modulus, I is the second moment of area, L is the length. So from these analytical expressions, I've estimated that the first and second mode of resonance are about 180 and 1100, okay, from the calculations that are included here. So let's go over here, and we'll look. Okay, still didn't. It's showing damped. That's interesting. Okay, well, it kept these. All right, that's fine. And we can see that the first mode, okay, is up and down, and that's around 200. All right, so that's not too far off. And also we should note that we added this amount of mass, all right, at the end, and we got rid of the stress concentration, but in a sense we've created a slightly shorter beam, and a beam that also has a slightly larger cross section, at least in this region. So that means that the resonant frequency that we have is going to go up. Okay. In terms of the the different modes, okay, you can come over here and you can click them, right-click them, create mode shape result. No. What is going on here? I'm having trouble with my mousing. Create mode shape. I don't really want to create. I just want it to. My mouse. I'm having troubles. Okay. Okay, retrieve this. I had to click on total deformation. Thank you. Okay, so when I do this, now I'm in the second mode. Now, this second mode, if we watch it, this is where the video is important. Look which way it's going. It's going side to side. Okay, so that's like if I took this beam and I ran the solution, then Hartog's formulas with now B and H flipped, this is what we would be getting. Okay, so that's not exactly that second mode that we're predicting, but let's check out the third. I retrieve this result. Okay, voila. This does in fact look like what Hartog is describing in his book. All right, which is right here. Okay, this kind of interesting bending mode. Okay, so, and that's at, we said 11:30, and we're saying 12:30. Okay, and again, that's because we have this additional stiffness here in part. Okay, now, what you would like to do as part of your assignment, okay, is submit a screenshot showing the deformation of one of these modes. All right, and then that will allow us to move to the last part of the assignment. Okay, where we're going to use the frequency analysis, okay, in Ansys. So often, right, when you're doing a job of trying to understand how structure responds to frequency, you're not just going to say, I only going to apply this frequency at a specific resonant mode, or at a, essentially at a frequency associated with a particular mode of resonance. What you'll have is a range of frequencies that are hitting the system. And if you want to see how to do that using like a power spectrum and using Ansys to do that, check out the tutorial from the Ansys Learning Forum. But for us right now, I'm just going to show how we can interrogate at a particular frequency. So if we were to hit this system with a particular frequency, what is the type of response? What is the amplitude of the stress that we would expect? Okay, so for doing this, we're going to go up to here, and this avoids having to go back to Workbench. And if you look at Workbench, actually, this is kind of fun. Workbench has been growing, okay, based on what we've been doing inside. So we go back here, and we'll add kind of console style. All right, we're going to add a harmonic response, okay, and we're going to need to once again do that fixed support. Okay, so we come over here, we're going to insert that fixed support on this face like that, hit apply to avoid grief, and then we'll go ahead and we will add a force. And this will be that transverse load. That's looking good. Hit apply. And this time I'm going to use a much smaller force. Okay, why? Because at near modes of resonance, I expect that I'm going to get a jump, okay, in the amplitude of the stresses that we have. So let's use the vector, and what? Oh no, not vector. I want to use components. There, here we go. All right, and we'll put in something kind of smallish. We'll put in 10 in this case. All right. And for the analysis now, we had to specify frequencies, all right, and that it's going to use. And this, it seems pretty straightforward, but it's actually been a little bit buggy when I coupled it with fatigue, at least for me. Maybe I shouldn't say that, but it's been a little bit tricky to get this to work right. So let's say that I'm interested in looking at things in the vicinity of that 200 hertz. Let's go like 190, okay, to 210, okay, and we're going to just use 3, okay. So you often, when you do, you do lots of, different frequencies, like what you see in the Bodhi plot that we were showing here, right? So, if you're trying to get something that looks kind of smooth, you're going to interrogate lots of frequencies. But here we can just do like that, okay? And then in this case, for the damping, it has this nice opportunity to put in a damping ratio, so we'll do that. And again, that it actually 0.01 I don't think will affect things that much here, okay, but that just gives you a little bit of idea, like, that it's bounded from going completely bonkers and out of control, okay. And then we'll go ahead and we'll look at solutions where we have the stresses. Okay, so the stresses of interest. Oops, mouse scene. Okay, like so. All right, and we should be able to run this solve without an issue. So it's going to look in the general area of 190, 200, and 210. And if you're going to do like a really smooth plot over orders of magnitude, you should use the logarithmic spacing, which is kind of what you saw in the MATLAB plot for that second order differential equation. Okay, and so when we do this, all right, now we see, okay, it did about 200, about 200 again, and about 210. All right, and what I typically, if I want a particular frequency, I put that frequency as the last one, and that's the one that Ansys seems to be giving me. Okay, but nonetheless, if I click here, okay, and I retrieve this result. Okay, I think it's already retrieved. Well, there you go. Okay, we can see that the stress, okay, the maximum stress is around 109 here. Come over here, retrieve this result. Okay, it jumped to 173. All right, at that frequency, and if we retrieve this result, okay, it comes back down, right? So we went through that resonance that we were seeing at about 200, okay? So let's do it interestingly, all right? Again, if you want a specific frequency, okay, you're gonna specify that as the like if you go back here, the specific frequency, that's the maximum one, okay? It seems to nail that one, but the other two are suspect, all right? And so now let's go ahead and we're going to add the fatigue tool. Now the fatigue tool also does something kind of interesting, okay? It, by default, will only show the value, okay, at the last frequency that you have here, okay? So this is going to be showing the value at 210. You can change it if you come under fatigue tool. You can insert a different frequency, okay, at which it does the analysis. But when it's the default, when it says 0 hertz, it's showing you the last frequency that you entered, okay? So this is interesting. What does this say there? Well, the equivalent stress that we had at 210 hertz was only 89 megapascals, right? Is that below the endurance limit? Well, yes, it is below the endurance limit, right? If we go back here, when we made our SN curve, right, what we said is our endurance limit was going to be, well, 1 times 250 megapascals, right? So that means that we expect the whole beam to have infinite life, all right? Now, so that's what we see here. But what happens if we go to this system? Well, I think we still will have infinite life, right? Because this max value is only 173, okay? So that's going to give us infinite life as well, all right? So if we go over to there, back to the life, okay? Again, infinite life. So what can we do if this is too boring? Well, we have multiple things we can do, but let's go ahead and we'll crank up the force a little bit. So if we crank up the force to like 30, okay, then we solve this system. And while we're waiting for this, okay, we can see that this is the last thing we need to do. You're going to have some frequency, and I might change this a little bit based on what I'm seeing in this video, but some frequency, some load, okay, and we're going to estimate the fatigue life, all right, there. So in this case, the equivalent stress is now much higher, okay, much higher, okay, at 30, all right, and the life now, all right, is significantly less. All right, so we have 1,881 seconds, okay, at 210 hertz as a minimum, or 47,000, okay, seconds at 210 hertz. Now, what does this mean? This is seconds, and it's probably good to say, well, before we were talking about life in terms of a number of cycles. Well, now it's giving us life in terms of number of seconds. So for this, all right, whoops, come on, MATLAB, yeah, okay, we have, if we're, and remember we're at the last one, so we're 210 hertz. If we take the maximum, that's 4762 times 4762, right, we get 1 million. All right, and that would be infinite life. So that's what you expect. But if, right, we have only 1,881 seconds times 210, okay, the number of cycles we expect is 39,000 or 395,010, okay? So that's going to be less than the than less than infinite life, right? 1 million is infinite life. And so if we go and we try a different solution, so we go to equivalent, so let's say I want to do it at 200 exactly. So what you got to do is come over to analysis, and we're going to drop this down to 200. So it's the second one, right? Now this one will allow us to see what that last value that defaults into the fatigue tool. Frequency's out of bounds. Okay, so if that happens, then what you do, which is annoying, is you delete this, which can happen, and it should now, okay, solution, information, okay, wow. All right, so let's see, we delete these. So it got corrupted. I've had this happen before. Okay. All right. Let's see here. Or we can just clear. Actually, yeah, just clear the generated data. That's what you do. All right, and now that's what. And now we'll run it. So at least we didn't have to redo the harmonic response and put in a new fixed support and a new force. Okay, and for the solution, we can insert our equivalent stress. Okay, and we're going to insert our fatigue tool like that, and then we're going to insert the life. Okay, and we can evaluate all these results. So don't have to do solve again. All right, and what do we see? Okay, that last one, once again, it's at 200. So it's that last one is the one that we get exactly where we want it to be. Okay, and then for life, look. Yes, in fact, we have an issue. Remember, that thing was springing up. Well, we can see it was springing up to like 850 megapascals. That's way above, all right, our predicted life. So now, or our predicted endurance limit and our 10 to the third endurance limit of 450 megapascals. So now the life, its min is a fraction. It's just a fraction of 1, okay, because it's going to fail, all right? So of course, we wouldn't want to operate our system at this frequency with this amplitude of force because it could lead to catastrophic failure. Well, and that's not just fatigue failure. That actually turns out to be just ultimate tensile strength and yielding and likely breaking as well. So for the final part of the assignment, you want to take a screenshot of something like this at the specified frequency and the specified load. Thank you, and I hope that you've got a little bit more perspective in terms of how we model, all right, how we model a cantilever beam, how we look at SN curves and we make predictions for fatigue life, how we show the effect of a stress concentration, and how we analyze modes of resonance, and how we can then induce vibration at specified frequencies. Thank you.